Hi, in today's video we're going to take a look at a Kaiweets HT118E 20,000 counts multimeter. For those who have been following my channel for a while, you probably remember that I did a review and teardown of a 6,000 counts Kaiweets HT118A multimeter a couple years ago, and I was pretty impressed with that meter for its performance and build quality, given its price. So when Kaiweets approached me a couple weeks ago and wanted to send in their newest 20,000 counts HT118E for review, I happily obliged, of course. If you are interested in getting one of these after watching the video, this meter is currently priced at around $48 on Kaiweets' website, and you can get 15% off using the coupon code provided in the video description below. Anyway, like most of the Chinese products, the HT118E is sold under many brand names such as Hubble Test. As long as the model number is HT118E, the electronics inside the meter itself should be identical to the Kaiweets that I have here, so this review should be applicable to all the HT118Es you see out there. First, let me put the 118A and 118E side by side, and you can see that 118A is on the left, whereas the right-hand side, that's the newest 118E. You can see that these two meters are virtually identical, at least from the outside, except, of course, for the model numbers printed on the top here. And the key difference in specs is that the 118A is a 6,000 count meter, whereas the 118E is a 20,000 counts meter. Both of the 118A and 118E are powered by two AA batteries, which is very convenient. And you can see the backside. Both are virtually identical as well. Of course, the label here is a different color, but the construction and everything, including the case material, are all identical here. Like the 118A, this meter also claims to be Cat3 1000 volts and Cat4 600 volts rated. I personally would not use these cheap meters in either a Cat3 or Cat4 environment, especially if that is my daily job and my life depends on it. But for general electronics work and in-house electrical work, this meter should be more than adequate, as we are most talking about Cat1 and Cat2 ratings in these scenarios. When it comes to a multimeter, the first thing that has a long-lasting impression on me is the range switch, as that is something that you use every single time. The good news is, just like the 118A, the range switch on the 118E is almost ideal. It is not too hard to turn, and has a very nice clicky sound, and it lands on the range very precisely. And if you have watched my other multimeter review videos, you will know that this is actually a very high praise for the range switch on this 118E, as I'm very picky when it comes to range switches. The display on this HT118E is also excellent. You can see the contrast and the viewing angles of this meter is great. The backlight looks very uniform, and I think they actually may have further perfected the LCD manufacturing over the years, as in my opinion the LCD on the 118E is ever so slightly better than that on the HT118A just a couple of years ago, and that one is already very good. I'm not sure if it shows up on camera here, but you can see from this angle the contrast on the 118E is actually ever so slightly better than that on the 118A. Especially at a steeper angle, the 118A fades out quite a bit. Let me put the 118A away and let's concentrate on the 118E for now. And if you press and hold the backlight button here, you will see that the flashlight on the back turns on. Now, I personally have never got into a situation that I would use the flashlight feature, but a lot of people commenting on my previous review video of the HT118A had said that they found this feature quite useful, as you don't have to hunt for a flashlight while you just wanted to see something that you are trying to measure. You probably have noticed that these jacks are lit when switching ranges, and they tell you which jacks you should plug the leads into. Of course, this is just a visual indication, and it doesn't really prevent you from plugging into the wrong jack. Nevertheless, it is a nice touch. The 118E came with this cardboard box, as you can see here, and also was shipped in the same pouch as the 118A, so you've got a thermal couple for temperature measurement and a set of stock leads. Now, if you look at it, the leads here are pretty stiff and definitely feel on the cheap side. but that's what to be expected for a 20,000 counts meter for under $50. They will definitely serve the purpose for sure. Now moving on to DC voltage measurements. For this exercise, I have few multimeters all measuring the same output from the EDC voltage standard up there, so I will just show you that. That's the EDC voltage standard to the left. The HT118E Plus is a 22,000 count meter, while the ANA70 is a 20,000 count meter. Well, it's a 19,999 counts, but for all intent and purpose, it's a 20,000 count meter, just like the HT118E. All three of these meters are considered 4.5 digits meters, and for reference, I have a 5.5 digit meter that is a Keithley 197 back there. So now let me start the voltage reference 1 volt at a time. 1 volt, 2 volts, and you can see essentially all meters are bang on. 3 volts, 4 volts, 5, 6, 7, 8, 9, 10. Let's just double check the specifications here, and according to the spec, the HT118E, you can see essentially all DC measurement range has an accuracy of plus minus 0.08% plus 5 counts. And you can see that the measurement essentially is bang on, which is definitely within the spec. And now let's take a look at the millivolts measurement. For that, I have set all the meters into the millivolts measurement range. And because all these meters actually have a 10 nanovolts resolution, so let's start with 10 nanovolts to see if we are able to register anything on the HT118E. 10 nanovolts. You can see that the only meters register that appears to be the ANA70 and the Keithley 197. Perhaps the HT118E also registered that, but we're not able to tell the last digit. 20 nanovolts. So it doesn't seem like we are able to register that on the HT118E. 30, 40, 50, 60, 70, 80, 90. It seems that the lowest the HT118E can register is actually around 90 nanovolts. So let's go back to 80 nanovolts. And nope, it can't register that. So 90 nanovolts is the threshold, it seems. So okay, so now let's start up with 100 nanovolts at a time. So 100 nanovolts, 200, 300, 400, 500, 600, 700, 800, 900, and now we have 1 millivolts. Let me just turn the dial to 1 millivolts. Yeah, no problem. Now let's start with the 1 millivolt increment. 1, 2, 3, 4, 5, 6, 7, 8, 9, and now let's do 10 millivolts at a time. 10, 20, 30, 40, 50, 60, 70, 80, 90, and let's do 100 at a time. 100, 200. So you can see that the millivolts measurement range is also very accurate on this 118E. While I still have all these meters hooked up, I wanted to take a look at the frequency response of the AC voltage measurement of all these meters. Now you can see that we are actually outputting a 10 Hz signal on the Unity HT118E and also the ANA70. They're all roughly showing about 1 volt, which is actually the output from the signal generator on the UTG962E. Now the only meter that is out is this Keithley 197. That's because the minimum measurement frequency is actually much higher than 10 Hertz. So now let me increase the frequency and let's see what we got here. 20 Hertz, you can see that immediately the 197 is also showing the correct number now. So 30, 40, 50, and by the way, it's very nice that the Kaiweets has this frequency reading on top of the voltage measurement. This dual display makes it very easy to read instead of having to change between frequency measurement and voltage measurement all the time. So let's do 100, and no problem. I'm going to increment by 100. So now it's 1 kilohertz. All the meters are reading accurately. Now let's change it by 1 kilohertz at a time. You can see that it seems that at 2 kilohertz we started to notice the drop. Let's increment it by 100 hertz at a time, so we will see at what point we drop below the 0.707. And it seems that 3 kilohertz is actually the bandwidth limit for both the Kaiweets and the ANA70. Of course, the other two meters have much higher bandwidth than these two. So the neat thing about this Kaiweets HT118E is that we have this frequency counter right on top of the voltage display. So at least you will know, for example, even when we have very high frequency here, you are not able to read anything here. Let's just see at what point we're not able to register any readings. Yeah, above about 7, 8 kilohertz that you virtually can't read anything, but we still have the actual frequency counter reading. So that makes measurement a lot easier because you know there's a signal presence, whereas the ANA70, you can't see anything on the display, so you don't know whether or not there is a voltage present at the input. Just for curiosity, let me keep increasing the frequency to see how high we can actually read the frequency on this voltage display here. Yeah, roughly 42 kilohertz. That's where we can measure the maximum frequency on this voltage display. So now let's take a look at the frequency measurement capability of this HT118E. According to the spec here, you can see that we are able to measure up to 10 MHz with an input voltage of 0.8 volt RMS. So right now you can see that we're outputting a 1 kHz 0.8 volt RMS signal from the UTG962E. That's the minimum specified voltage we can measure up to 10 MHz. And let's take a look at how high we can measure with this Kaiweets HT118E. And I really like the dual display here. You can see that when we're measuring the frequency, you can also see the duty cycle. Now, of course, we're inputting a sinusoidal that is expected to be 50% duty cycle here. So now let me change the UT61E plus to measure frequency as well, as we are using this as a reference here. So now you can see that both meters are reading about 1 kHz. Now let me just increment it to 100 kHz so that we can start from there, as I am expecting it will be able to measure well beyond that. So let's do 100 kHz at a time. 200, 300, 400, 5, 6, 7, 8, 9, 10. No problem. So now we're measuring 1 MHz. Now let's start incrementing 1 MHz at a time. 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is our specified maximum measurable frequency here. Now you do notice that while the frequency measurement is accurate, the duty cycle measurement is actually not. So right now we're still in that sinusoidal mode. So we should be reading 50%, but you can see that it drops to 38.1%. Now that shouldn't be an issue for frequency measurement. So let's keep increasing the frequency to see exactly how high we can actually measure using this HT118E. 11. No. So by the look of it, 10 MHz is actually the highest, and we can probably squeeze a little bit. Let's do 10.1, 10.2, 10.3, 10.4, 5, 6, Yeah, we can definitely achieve that 10 MHz maximum specified frequency range based on the specification, but the margin is pretty tight. So what I'm going to do right now is to increase the output from the HT118E, as right now we're at 0.8 volts RMS. So let's take it to 1 volt. And you can see immediately we're able to measure that frequency again. So now let me start incrementing the frequency and see if we can get any higher here. So now let's just get to 11, 12. So no, it doesn't seem like 1 volt is able to push the measurement range any higher. Let's do 2 volt RMS. And again, now the reading comes back. So let's go back and increase the frequency again. 13, 14, 15, 16, 17, 18, 19, 20. Of course, we won't be able to measure 20 as this is a 20,000 count meter. So let's drop it down a little bit so we can measure it. So yeah, so right now we're actually outputting a 19 MHz 996 signal. So basically this tells you that if the input signal is of a sufficient amplitude, you are able to measure up to 20 MHz with no problem. Next, let's take a look at the mains voltage measurement. For that, I have hooked up both meters to a variac. Now let me start increasing the output from the variac and we'll see what the readings are on these 2 meters. And you notice that the update rate from the Kaiweets actually is pretty fast. And if I stop here, you will see that the readings between the 2 meters, they agree with each other. So let me keep increasing. And again, I think above 20 volts, the UnityUT61E will show you this symbol here, which means it's high voltage you need to pay attention to. But on this meter, we haven't seen that yet. And let's keep increasing the voltage. And it seems that at about 80 volts, this is where the Kaiweets started warning you. And the way it warns you is with this orange backlight. That is really nice touch in my opinion. So let's keep increasing. Now I'm just going to increasing to the maximum here. And you can see that these 2 meters largely agree as well. And by the way, according to the spec, the AC measurement accuracy for the Kaiweets HT118E is at 1% plus 25 counts. So we did see some discrepancies between these meters, but nevertheless, that is still in spec. While we still have that variac up here, I wanted to test the non-contact voltage measurement capability of this Kaiweets meter. So let me turn it to NCV and let me bring in the live wire here. And you can see that as we move closer, the beeping becomes more rapid. So that is definitely very sensitive and very useful here. Next, let's take a look at the DC microamp measurement range. If you look at the specification here, you will see that the accuracy is specified at 0.5% plus 5 counts. For that, I have my 100 microamp current standard. Let's take a look at how accurate this meter is. And you can see that we're definitely within spec. Now let's take a look at the milliamp range. For that, I have put these 2 meters in series and outputting a current from the HT118E. So let me increase the output current. And again, you can see that if I just stop moving the dial, you can see these 2 current readings are largely in line with each other. And let me just increase to the maximum. And you can see these 2 readings are largely in line with each other. Again, because we have that 0.5% plus 5 counts, therefore the readings are definitely in line with the specification. Now let's take a look at the DC amp range measurement. If you look closely, you will see that on the Kaiweets HT118E, you have 1 extra digit compared to the Unity UT61E Plus in the amp range. This is actually very good, as you will be able to discern a 0.1 milliamp current on this HT118E. This is actually very useful if you are measuring a current. Let's just say you want the ballpark and don't want a lot of voltage drop. You can use the amp range to measure your current. That will have a very low burden voltage. Anyway, to test this range, I'm just going to use a DC power supply, and I'm going to enable the output. And right now we have about 0.15. It doesn't really matter the actual reading, but you can see that two of these meters are largely agree with each other. So now let me increase the current. Let me increase it to 1 amp. And I'm going to increase it 1 amp at a time. So you can see that at 1 amp, we can see that backlight started turning on. That indicates that it's a high current situation. So let me keep increasing the output current. Okay, I'm going to increase it 1 amp at a time. And you can see that once we hit that 10 amp mark, we started beeping on this Kaiweets meter. That means it's a overcurrent situation, as the maximum current you can measure on this meter is 10 amps. One thing I forgot to mention earlier is that the Kaiweets HT118E does come with a bar graph, but the bar graph does not update in real time. You probably have noticed that in my previous demos, but let me just show you here. So for that, I'm hooking the meters up to a variable power supply, and I wanted to pay close attention to the bar graph on the unit T versus the bar graph on the Kaiweets. So now let me adjust the power supply output. You can see that we're not able to catch up with the actual voltage change on the Kaiweets HT118E. Now let's take a look at the resistance measurement range. And you notice that the range switching is actually pretty slow. So let's short the leads and take another look. Yeah, it takes quite a few seconds for it to register the actual reading. And one thing you notice is that we actually don't have a rel button in the resistance measurement mode. Ideally, you need one, especially if you are measuring low resistance. As you can see that the leads resistance are actually not zero. But in this case, we actually aren't able to rel that residual reading out. So we'll just have to do it mentally to kind of subtract that 0.05 of the actual reading. First, let's take a look at a 100 ohm 0.1% tolerance precision resistor. Of course, this meter is a 1% accuracy meter, so this 0.1% resistor is an overkill, but nevertheless, let's try it. And you can see that by subtracting that 0.05, we are able to get a 100, well, 115, 102. So that is definitely within the 1% accuracy range. And let's take a look at another resistor. And this one I have here, let me just see here. By the look of it, is a 100 kilo ohm resistor, and this one is a 5% tolerance. So we should have no problem measuring it. And yes, we're reading 99 kilo ohm, so that is definitely within the accuracy range. Although the auto ranging speed is on the slower side for this HT118E, it does have a key advantage here. That is, it is able to measure resistance up to 100 megohms. Now, I don't currently have a resistor of that high value, but I can just show you here with my hand. And in wintertime, they're relatively dry. So you can see that if I just touch lightly, we are able to get a pretty high resistance reading here. And let me see here. You can see that we're definitely above 20 megohms. So that is a very high resistance. And we are able to measure that with this HT118E. Now let's take a look at the continuity measurement mode. And you can see that is pretty fast, and the measurement is certainly latched, so no problem at all. Now let's just take a quick peek at the diode measurement mode. For that, I have a white LED. So let's do a quick test here to see if we are able to light it up. Yep, no problem. But we're not able to read the forward voltage drop of this LED. So let me bring in another LED just to take another look. Here I have a red one. So let's take a peek. Yep, so by the look of it, we are able to measure the forward voltage drop of a red LED, but not the white one. Now let's move on to the capacitance measurement mode. Again, because we don't have a rail button, so you cannot zero out the residual reading. Because we have these long leads, you won't be able to measure very small capacitance accurately. So that's unfortunately a drawback. But we should be able to measure a 100 nanofarad capacitor with no problem. Remember, this one we measured last time is about 70 something, 73, yep. So that is clearly accurate enough, and the speed is pretty fast. So let's measure a larger capacitor. This one is a 1 millifarad. So let's take a look at how fast we can get this one measured. And you can see it took quite a few seconds, which is normal for large capacitors, but it is not the slowest for sure. So no problem at all. Lastly, let's take a look at the temperature measurement using the built-in thermocouple. Of course, if you want to measure the external temperature, you can use the supplied thermocouple and plug it in. You should be able to measure temperature outside. Now it's reading about 65 degrees Fahrenheit, and that seems to be a little bit high for the lab. But again, you can see that the temperature accuracy is specified at 1% plus 4 degrees. So that probably is going to be in line with the lab temperature. If I remember correctly, actually let me bring up the 118E. Hang on. Yep, so 118A, you can see that the display is the other way around. We have the Fahrenheit down here and the Celsius up there. So it seems like on 118E, this display is swapped. Now moving on to the teardown. The holster is a little bit plasticky and was pretty difficult to remove. But anyway, so now that is out of the way, let's open it up. And this is the back of the case. I have removed the battery cover. You can see that we have the two AA batteries. And the batteries are essentially pressed on to the main circuit board via these two spring-loaded contacts. So that is a very neat design. Now let's take a look at the main board. If you have watched the teardown video of the HT118A, you will see that the layout and the circuitry on the board inside this HT118E is almost identical to that of the 118A. So the only difference would be just the main DMM chip, and also the display chip. I think the mounting location is slightly different than that in the 118A. I will pull up a picture of that teardown video here, and you can compare it by yourself. And just like the 118A, you can see that the input side doesn't really have a lot of protection here. We have two of these PDCs, that's about it. For a Cat3 and a Cat4 rated multimeter, typically you will see some MOVs at input because of the high energy circuitry you are trying to measure. In the event of a transient, those are there to absorb the excess current during an over voltage situation. And also you notice that in the input section, we don't really have any high voltage cutout. So because of this, in conjunction with the no MOVs, I would certainly not use this in a high energy Cat3 or Cat4 situation. Here is a close-up view of the input section. You can see we have a current shunt resistor for the 10 amp range. And we also have two resistors here for the lower current range. And by the look of it, one of the resistor is a 100 ohm resistor and the other one probably is a 1 ohm. I can't really see from this angle, but that is the current shunt for the lower current range. Here we have some protection diodes, and we also have two of the fuses for the two current measurement ranges. Here's the view of the upper portion of the circuit board. You can see that we have the main DMM chip right here. Unfortunately, the markings are sanded off, so I don't know exactly which chip they're using here. And here, this 8-pin chip, that's a 24C02, which is a 2K I2C EEPROM that is used to store the calibration and some other settings for the DMM. And here is another chip we also don't have any markings on, so your guess is as good as mine. I'm guessing this is probably either a shift register or a logic device that is handling the keyboard and some other glue logic. And finally, we have this larger chip here. This is a HT118E. that is a Holtec 32x4 LCD controller. This metal tab here is for the non-contact voltage detection. And as I expected, the other side of the board looks pretty much identical to that in the HT118A. There's not much on it. I almost forgot to point out a neat design feature here. You can see we have 4 LEDs mounted on this PCB here, and these matches the light guides on the front of the case, and these essentially get routed to each of these input jacks, and they light up depends on the range you are currently in. Now that wraps up the video. All in all, I think the HT118E is an excellent meter for the hobbyists given the price and its performance. At less than $50, you really could not have asked more, feature-wise. If I have to pick out a few shortcomings, one would be that it does not have a relative mode for low resistance and low capacitance measurement modes, especially given the high resolution this meter offers. And I'm not sure why that feature was omitted in the design, as I'm sure that it was fairly simple to include, as the DMM chip definitely supports it. It is by no means a deal breaker though, as you can always subtract the residual readings by yourself. Another thing is the resistance measurement mode speed. It is by no means fast, but in the price range, the speed we saw is fairly par for the course. Anyway, I hope you enjoyed this review and teardown video. If you liked the video, please be sure to give it a big thumbs up and remember to subscribe to the channel for more videos like this in the future. I will catch up with you next time.